What was our topic of discussion last time? Yes, please answer. Many students have not replied. What was our last topic of discussion? Yes, please. Yes, please reply. Many 6 students have not replied, please. We have few students, those who have not replied. Akepam, Prabjot, Pooja Nain, Simranjeet Kaur has not replied. I'm also sharing responses with you so that we have an idea what we are doing right now. So yeah, you can see that many students have also replied wrong. Okay. So it was spectroscopy, which spectroscopy, FTIR spectroscopy. Yes. So let's have a quick look. And these students, they are still thinking that we have lead or RHEED or SEM. Nobody has replied. Okay, anyway, we would like to come to our point and discuss that what is the meaning of the different terms which are there. Okay, so we would have this information with us. Let me pull out. So if you recall what we have done last time, we tried to understand that what is an FTIR spectrometer, how does it work, what is the basic principle of the FTIR spectrometer. And during this, what we have done that we tried to understand that what is the experimental layout of this FTIR spectrometer. And we came to the conclusion that the Michelson interferometer is an integral part of this interferometer, which we have to understand. And the first question is why we need to have FTIR spectrometer. The answer to this question is that if you have visible radiations which are incident onto the sample, in that case, what you can do, you can probe the electronic levels. Okay, for example, if you have the valence band and conduction band, you want to know about the band gap of that material, you will prefer the UV visible spectroscopy. On the other hand, in case of the molecules, you have the rotational and vibrations which are responsible for the spectra of these molecules. So in order to excite these the rotational and vibrational levels, we have to go for the FTIR. And the main thing is that what is the incident radiation, what are the sources which you are using in this case, and what is the sample. So if you look at the infrared range, so any wavelength which is above 700 nanometer wavelength, these are called the infrared, and then it spans over like 50 micrometer, the region, which is known as the far FIR, this is far infrared region. So in that case, you would have most of the molecules and the materials have their fingerprints or the signatures in that region. That's why we are using this FTIR spectrometer. Once again, why do we prefer infrared spectroscopy? The answer to this question is that the energy which is there for the infrared radiations. So what you do with the help of the infrared radiations, that these are incident to this, the surface of the sample. So what will happen in that case, that the infrared radiations have very small energy. If you calculate that in terms of the E is equal to h nu, so what will happen, it will come out to be small energy which can excite your vibrational and rotational levels of the molecules. So that's why we cannot use the visible source in this case. And second, the word which is referred to the Fourier transform in this case. What is the meaning of the Fourier transform? What is the physical meaning of the Fourier transform? The Fourier transform is a mathematical operation which can convert the time domain information into the frequency domain information, and vice versa also. That if you have a frequency domain information, it can convert into the time domain information with the help of this. So what happens in case of the FTIR spectra, once we obtain that spectra from the experimental configuration which is there, after that we have to process that, and a mathematical programming is done in order to get that information in terms of the transmission versus the wave number in this case. Okay. So let's pull out the information which we would like to have today for you. that the points which we would like to discuss. Let's have, okay, first of all, I would like to stop sharing your audio. Okay. So if you have questions, you can raise your hand, paste in the chat box. We can also enable voice for you. So let's come to our point now. Okay, so I'm just getting this point from here, and we'll come over there. Okay, so where we have left our lecture, that we have also to see. We have to also see that where we have left our lecture, and that is an important point which we have to look at. So I'm also pulling that information for you. In the meantime, we can start with our um, sharing of the screen. So I'm just pulling up to share screen with you guys. Okay, now we are sharing screen, and okay, so we are here on this screen, and let me. So our topic of discussion is again the FTIR, but in a better way and in the better sense. Okay, because most of the students, they will find difficulties when they are doing their dissertation or their research in case of the FTIR spectroscopy, because many students, they don't know what are the sources, what type of the sources are to be used, what are the beam splitters which are to be used in this case. So it would be good lecture for those who are performing the research, not only research but fundamentals, because this is a core subject which is to be studied by all of the students irrespective of your discipline. If you are having nuclear and particle physics, still they use FTIR spectra in many cases. If you are electronic student, then also you use it. And materials science students, of course, they are always involved in the FTIR spectroscopy. Okay, so even for example, across the discipline like chemistry or other departments, the bio departments, they use this FTIR spectrometer. So let's see that how we would like to come to this point today. So if you recall what we have done, let me pull out that information for you, and we would like to have this listing for you. So that's what we have done. One time. So here, the what we have discussed, that the integral part of the FTIR spectrometer is a Michelson interferometer, which is nothing but you divide the incident beam into two parts. No? So what will happen in this case? We have came to a conclusion. Okay. So let me pull out this information for you, and okay, I can make it like this so that we have both screens to share with. Okay, so we have this. If you look into the details of this setup which we have seen in this case, let's have a quick look that what is the main aim in this case. You have this source, which of course you are using in this case, and source, what kind of the source you need to have? These are the sources which are infrared radiation sources. And in most of the books, you will also see that here they will put a laser like helium neon laser. So the purpose of the putting laser is to align the setup. So what happens that in this case the the incident beam, which is in terms of the helium neon laser, that will align your setup. No, so that is only for the alignment purpose. And after that, you put your IR source, which is required for the sample. No? And if you look at here, what we have seen that if you would like to come to this point, at this point, you will place, you will see that the path, these OM and OS, these must be equal. And it cannot be equal unless and until you put this this beam splitter. Okay, when you are putting this, then the ray which is going to the moving mirror, that travels a different number of times, which goes through different number of time from the beam splitter, and this goes different number of times to the beam splitter. And somebody will ask a question that why to make them equal. The answer to this question is that in case of the optics, what happens that these two paths must be exactly at one point. Okay, either they should be at the same optical length or optical separation, or what they should be at the integral or half integral multiple of this separation. So first task is to find out the separation which is like the same separation. So for example, what you will do that you will you will do that, let's say that what you are trying to do in the case of the beam splitter which you are trying to talk about, somebody will understand that how they can understand in this case. So you would have this, let's say that this is the beam splitter. Okay, now what you are trying to do, you have a beam of light which is coming from here. Okay, then it will go there, and beam of the light which is going to this direction. Okay, and what will happen here, you have the mirrors. Now for a layman, what will happen, these two distances will be equal. Somebody will say that these are equal, but for a person who understands the optics in a better way, these are not equal because of this glass which is incorporated over there. So what you have to do this, because what you do that in this case, your beam is delayed. Okay, the velocity of the light which is there in the free space in this region, that will be different in the region when it is going through the beam splitter. So what will happen, these two distances will not be equal in this case. In order to make them equal, you have to introduce a compensating plate in this case, so that your beam which goes to movable mirror, that crosses thrice the beam splitter, and then which goes to 3, this level, this stationary mirror, that also crosses thrice in this case. So the overall aim is to make these two paths equal. You can also make them without placing this beam splitter by changing the position of this mirror, but it is a bit easier to measure the distances when you are placing a compensating plate in this case. So what will happen in this case, that after this point we have seen that we have introduced this beam splitter, and in that case, okay, both of the rays, they are going through the same optical elements, and then you would have equal path lengths in this case. Okay, okay, so let's give a simple example. If you have, let's say that this is a point A, okay, this is point B, you know? So what you are trying to do, this is a point A, and the second point is this, the second point is B. So if you look at these 2 points, somebody will ask a question from me that what is the distance between the points A and B? Okay? What is the distance between these 2 points A and B? I will say that this is equal to, let's say this is the 4 centimeter. Okay, but now what you have done, you introduce a beam splitter in between. Okay, now you are saying that, okay, is it 4 centimeter? No, it won't be 4 centimeter. Okay, geometrically it will come out to be 4 centimeter, but when it goes for optically, it will not be 4 centimeter in this case. Why it will not be 4 centimeter? Because you have additional glass in this case, so the velocity, the speed of the light, that is reduced. So this path length, which is 4 centimeter, this is not actually 4 centimeter in this case. Okay, that you have to understand from one or other point of view. So now, if you have any question, please don't hesitate to talk to me. Okay, there's no question. Okay, so what we have done here, okay, in the end, we told you that when they overlap, that's a very important factor, okay. What we have done, so we have tried to understand that many times it goes. So this beam splitter, I think that point is very clear, okay. I don't want to repeat that again and again. But this point, which is next point, is important. So when the interference will occur, there was one of the question, one student was asking that what we will see on the detector, okay? So what we will see on the detector, that we have to take into account, okay? On the detector we will see the fringes, okay? The detector will detect that signal which is in terms of the fringes, okay? How the fringes are generated in this case? But this is somehow not sure. Okay, what is here? So at the detector, they will give us the fringes. The output of the detector would be like this. So you would have fringes like this, okay? This type of fringes, and this will be detected. So you would, but the detector will see that as the response of intensity versus the wave number. Wave number. Okay. So that was the point here. I would like to again stress this. When you will see the constructive interference and when you will not see the constructive interference, when there will be destructive interference. From this curve, the along y-axis you have the intensity or the transmission, and along x-axis you have the retardation. What is retardation? Which we have seen in this case. What is along x-axis? That we have to make it clear. Okay. So what is retardation? That is equal to 2. That is equal to 2 OM minus OS. Okay. So this is this distance which we are talking about. For example, this the distance between these two, that OM is this one, this distance, and this OS this distance to the stationary mirror in this case. Okay, so when you are along x-axis, you have this delta. So this when it is the half integral multiple of lambda, in that case you would have destructive interference. When it is integral multiple of lambda, then you would have constructive interference. Okay, let's see that what we are talking about. I'm talking about these peaks. Okay, if you look into the details, right now I'm talking about this. No, for example, this is the minima. Okay, in this graph, what you would have, this point is minima point. This point is minima point, and this point is maximum point. This point is maximum point in this case. What you are trying to do, this maximum point is corresponding to the constructive interference, and the minimum point, which is words which I have shown to you, that is the destructive interference in this case. So you would have your pattern which you are observing on the detector, that will go in this fashion. Okay, first you would have the maxima, then you have minima, and then it goes like this one. That's the thing which we have studied here overall. Now next task would be that we have to understand in a better way that what we would like to do in this case and how it would be beneficial for us. So let me erase this part which is there. So let's have a look at the point, and okay, this is again FTIR spectrometer. So we should not forget our topic of discussion. So what is happening in this case? Let's find out that this how this resolution. If you want to get the first task would be that we would like to talk about the resolution, and we would like to talk about the Fourier series. Okay, Fourier series, Fourier series, a little bit. And after that, we would like to come to the point where we would like to solve the problem of the molecule. Take an example of molecule. Okay? an example to understand FTIR, to understand FTIR data, understand FTIR data. Okay, so what would be our idea in this case? So we have to make that clear. So can you tell us, so what the mirror, the movable mirror that is scanned, being scanned, okay, and it is scanned quickly, and the resolution of the spectrometer that depends on the scanning of this mirror, which is the movable mirror in this case, no? So how this mirror can, let's see that. Let's say that if you have the mirror which is the distance traveled by the mirror, or the retardation, if it is like the 4 centimeter, okay, 4 centimeter, okay, in that case what you will do, if it, the retardation, if it is 4 centimeter, we have also multiplied 2 in one of the patterns. Okay, let's see that. Okay. We were talking somewhere that the delta is 2 om minus os. Why we have multiplied 2? The reason for that is that the ray of light once goes to the mirror M and it is reflected back. Okay, so that's why we have multiplied with 2, because it's the double length we actually come across when it goes to the detector. Okay. So then what we would have, for example, if you have 4 centimeter of the retardation, then the resolution of the spectrometer, what it would be, resolution of the spectrometer, that will be equal to 1 by 4. Okay, so centimeter here, so it will be equal to 0.25 centimeter inverse. Okay, so sometime in case of the FTIR spectrometer, we also deal with these units, which are the units of the wave number. So that will be the resolution of this the Fourier Transform infrared spectrometer. But nowadays, okay, this is very quite rough distance which you are talking about resolution. Nowadays, okay, nowadays you can also go, if you go to, okay, it would be like 0.001 centimeter inverse. Okay, until that point you can go nowadays with the help of the best specters which you have. Now, if you come across what is the role of the Fourier series, let me write it. Okay, here we have fx is equal to, we are pointing out n is equal to 0 to so it is n is equal to 0 to infinity, and what you are trying to do, we are writing it a n sine n omega x plus b n cos n omega x. Okay, we are writing about the Fourier series, okay, expression, and let me put that in the parenthesis in this case. Okay. So what you would have in this case, that if you put here in this the expression a0, then you would have sine of 0 omega x plus b0 cos of 0 omega x. Okay, and then plus, when you put 1, then it will be a1 sine of 1 omega x. Okay. And then you have plus b1 cos of 1 omega x plus so on. So if you look into the Fourier series, then what will happen, that this Fourier series tells us that if you are having higher of the terms in the Fourier series, let's say that if you are having 0, 1, in that case what will happen, the fit to the the curve, that will be raw fit. Okay, if you are increasing the number of the terms in the, let's say that if you are going 2, if n value goes 1, 2 and 3, or in that case you are very close to the fitting. For example, if you are working like this, if you have a series function like this, then what you are trying to do, you have this value which you are trying to do. Let's say that if you have a curve, okay, like this, then if you have a, I am fitting it, okay, if you have less number of terms, in that case how your fit will look like, it will look like quite rough. Okay, for example, this is for n is equal to 0 and 1 when we have considered only 1. But in the second case, if you, the blue one, if you increase the number of the terms, that case what will happen, you would get the exact fit in this case, okay, for the curve, okay? For any curve which you are considering in this case, okay, let's say intensity versus the x, okay, okay, or fx, pattern fx versus x in this case, okay? So that we have to understand from this point. So what is the omega? Omega is the frequency, and if you go to the physical significance of the Fourier series function is that with the increase in the number of the terms, you are going to the better fit of that function. Okay, well, initially it will be rough. For example, if you are taking only a0 and b0 term, or if you are taking only a1 and b1 term, in that case it will be pretty rough estimate of ours. Okay, now let's come to the second point, what we would have in this case, okay, that about the second point which we would like to understand, which is an example to understand FTIR data, okay. So before understanding this one, or I think it would be better to have the second point with an example, otherwise you will not be able to understand what is happening with the system itself, okay. Okay, let me find out that point for you guys. So example. I would like to take an example of the formaldehyde molecule. What is the formaldehyde molecule? This is C double bond O, and here you have H, and here you have H. So this is a molecule which we would like to understand with the help of the FTIR. That, for example, if you carry out the FTIR spectra of this molecule, then how does it look like? Okay, and it would also be helpful for us to understand that this formaldehyde molecule, how it absorbs energy and how it releases energy in this case. Let's find out it. Okay. So what we have a simple setup. Very simple setup, not very complicated like Michelson or any other setup. So what I'm here, we have this one point. Here we have a source, okay, and here we have a detector. Okay? At this point, we have a detector, and let me write it here. Okay? So for example, here you have the source which you are considering in this case, and here you have the detector. Okay? That's the basic configuration, okay, of any spectrometer which you study. And here you have the molecule, which is, okay, molecule means that I'm putting the chemical formula of the molecule here, but entirely it is not one molecule, but it will be the combination of all the molecules which will be forming your material. Okay. So now let's say that this molecule, we can approximate this molecule like this. No? I can O, I would like to put it like this, no? O. And C, I would also like to put like this, no? Okay. And the double bond, I would like to replace that double bond with the single bond. Then it would be easier to understand that how does it work. So how it works actually, if you look into this and what we have done, that what are the possibilities? It can, this molecule can can vibrate. Okay, can, how it can vibrate? It can vibrate like this, no? Okay, it can vibrate like this. So this is called the vibration, stretching vibration. So it can, how it will be, you have the two balls and they can come like this. Okay, if then when they absorb energy in this case. Okay? The second possibility is that this is called the stretching vibration. Okay, stretching vibrations. And what is the next possibility? That here it can also this way. Okay, it can also, this is called wagging. Okay? What is this? This is called wagging. So for is wagging. Wagging means that, for example, when you it's especially related to the dogs. When you want to feed them, if you love them, then this dog will try to express his or her love to the owner by moving his or her tail. Okay, its tail. Okay? So that wagging means that, okay, it will just it will move the tail to show the love to the owner. Okay? And in the same way, what your molecule can also do like that, wagging. That is the second term, which is known as wagging. So if you have, let's say that this the stretching, let's say that once it go, if you have a molecule like the two dumbbells like this, so when they go once, okay, and then they come back, okay, that will be corresponding to 1 hertz. And then if you it goes like 2 times, then in that case you will say it is 2 hertz. The frequency of the vibration, that is 1 hertz or 2 hertz, depending that how does it stretch and vibrate in this case. No? So your molecule, which is here in this case, so let's say that, okay, if it stretches, for simplicity I'm looking at 2 hertz. So the frequency of vibration stretching is 2 hertz. Okay, it is 2 hertz. So what will happen in this case? You have a source and a detector. Now what you have done, that you start with the source which you have here. Okay, the source which is there. So what you have done, you have given 1 hertz. No? 1 hertz. For how much is the frequency? It is 1 hertz. Okay, and now the vibrational frequency of this molecule is not 1 hertz. It does not absorb any energy at 1 hertz, but what it will do, so all the light which is coming from the source, that will go to the detector. Okay? So if you ask the detector, can you tell me that when I have thrown 1 hertz light, what is the light in your, how much light is there? Then it will say 100%. You would have 100% light. Nothing is being absorbed by the molecule. But in the second case, what will happen, that you would have the, now instead of, let me represent it with the red one. Okay, what we are trying to do now, you would have, okay, what you are trying to do, you would have a second ray of light which is 2 hertz. That one is 2 hertz. Now what it will do, okay, the molecule will see, oh, 2 hertz is coming. Now it is set to have, it can absorb that energy in this case. So you will ask the detector, I have sent 100% of the light from the source. What is light which is received by you? Detector will say 0%. I have not received any light, because all of the light that is being absorbed by the molecule itself. I hope that this thing is clear. Now, what will happen? That let's say that, okay, 4 hertz, the wagging, this wagging frequency is like 4 hertz. No? 4 hertz. It absorbs, the vibrations are like this one. Okay? So if you have vibrations like this one, in that case it is 2 hertz. Okay, it absorbs the energy at 2 hertz. But if it is wagging like this one, in that case it is giving you the energy which can be absorbed at 4 hertz. Okay, the same thing. And sometimes what happens with the molecules, sometimes they don't absorb completely the energy, they absorb partial energy in this case. Can we just try to make a graph of this? That will be helpful. The same situation, okay? Let's try to make a graph of this. So what will happen in this case, you would have along y-axis, what you would have along y-axis, and what you would have along x-axis. Okay, along x-axis you would have the frequency, which is in hertz. No, along y-axis you have percentage transmission. So let's can you tell me that here you have, let's say that this is 100%, this is 100%, this is 50%, this is 50%. Let's say that here you have 0% transmission. So then let me, the first frequency which I have thrown here, okay, here you have 1 hertz, here you have 2 hertz, here you have 3 hertz, here you have 4 hertz, okay, and here you have 5 hertz. So how will do that? That ask me question, when what is the value of the transmission at 1? Okay. It is 100% because the molecule won't absorb the energy because its own vibrational frequency is 2 hertz. So let me put this point here, 100%. In the second case, the 2 hertz, when I signed a light whose frequency is 2 hertz, in that case, what is the value of the which is detected by the detector? That is 0. Let me put that point here. In the 3 hertz, what is the value when I am putting it? It is again 100%, 100% transmission because it won't be absorbed. In 4, let's say that it is partial. Then how my curve will go? I will attach it like this. It is going like this, and then this, then this. Okay. So this is the actual spectrum which is being viewed with the Ftir spectrometer. If you look into the now, people will say that, okay, when I have looked at the data which was given by the experiment, I didn't see anything like this. So this thing is not there. Okay? Let me find out that what is the actual spectrum in this case. How does it look like? Okay. So the actual spectrum looks like this one. What you would have in case of the actual spectrum, same. The x and y will be the same. Okay, hertz, and here you would have the percentage transmission, and the spectrum will look like this. No? So the spectrum will look like this. The spectrum will look like this one, okay? The actual spectrum. And this, for example, if you have a molecule, for each of the molecule, you would have a particular spectral fingerprint in this case. Okay, so what will happen if you are having this one? You will look at the molecule and you will see that, okay, what is the value of the absorption or transmission at this value, okay? So you would have this one. And okay, so let me emphasize here, instead of frequency, you would have wave number, okay? But they are interrelated, don't worry about that, okay? Wave number, whose units are centimeter inverse in this case, okay? So wave number is nothing but it is equal to 1 over lambda, okay? So that's the unit in the units of 1 over lambda in this case. What we have learned today, we try to understand what is the meaning of the Ftir spectrometer, how does it work? If you come to, we talk about the resolution. Resolution depends on the scanning of the mirror. Don't hesitate to ask me questions. That will be real thing which we can do here. Yeah, I am enabling your voice. If you have quick questions, please answer the questions. Ask questions, please. Any question? I have enabled your voice. Everybody can talk right now. Okay, so what we are trying to do with the help of this one, that okay, we have the resolution which we can calculate, which depends on how fast is your mirror, movable mirror is scanning. This is the Fourier series which tells us that how the fitting function that increase the accuracy in this case. And this is an example that how the energy is absorbed and transmitted when you would have actual spectrometer in case of the news, to understand that every molecule would have a particular frequency that it will absorb, and it is known to the people. We have drawn a rough spectrum. The actual spectrum will look like this one. Actual spectrum will look like this one because you have many frequencies which will be there. Any question, please? Any question? Any question? Any question? Okay, then I would like to suspend the session. Can leave the session.